Hey there, science fans! Ever looked at a super fast race car, a giant airplane, or even your trusty bicycle and wondered, what's this thing made of? It's a great question, and often the answer involves a choice between two amazing types of materials, metals and composites. Which one is better? Well, that's like asking if a hammer is better than a screwdriver. It all depends on the job you need to do. Today, we're going to dive into the fascinating world of these materials. We'll explore what they are, how they're different, and why engineers get so excited about them. So, buckle up, because we're about to engineer some understanding. Alright, let's dig deeper into metals. Metals are elements that readily lose electrons to form positive ions, and they have a characteristic crystal structure with a sea of delocalized electrons. This electron sea gives many metals their excellent electrical and thermal conductivity. Think about how quickly a metal spoon heats up in hot soup. That's conductivity in action. Common examples include iron, aluminum, copper, titanium, gold, and silver. Metals are known for their impressive strength, ductility, and malleability, making them ideal for various manufacturing processes. They also have good toughness and high melting points, making them suitable for high-temperature applications. Now, let's switch gears and talk about composites. These are engineered materials designed for specific superpowers. A composite material is made from two or more constituent materials with different properties, producing a material with unique characteristics. The two main components are the reinforcement, often fibers like carbon, glass, or aramid, and the matrix, typically a polymer resin like epoxy or polyester. Composites are known for their high strength-to-weight and stiffness-to-weight ratios, making them incredibly strong and light. They also offer excellent resistance to corrosion and can be tailored for specific properties by controlling the type, amount, and orientation of the reinforcement fibers. This allows for highly optimized structures, which is pretty neat. Section 4. The Great Material Showdown. Properties, uses, and tough choices. Let's put metals and composites side by side. For strength, both can be very strong, but high-end composites often win on strength to weight. Composites are generally much lighter than most structural metals like steel, though aluminum and titanium are lighter metals. Composites can be engineered to be incredibly stiff for their weight. Cost is a big one. Common metals are usually cheaper, while advanced composites are pricier. For fatigue resistance, composites often outperform metals, especially aluminum. And for corrosion resistance, composites generally have a big advantage over most steels, though stainless steels and titanium are very corrosion-resistant metals. Metals are everywhere. Steel is the king of construction, aluminum is a star in aerospace, and copper is essential for electrical wiring. Composites shine in applications where their special properties give them a distinct edge, like aerospace, high-performance sports equipment, wind turbine blades, and marine applications. Engineers choose materials based on loads, operating environment, manufacturing, cost, and maintenance, balancing these factors to find the optimal solution for each engineering problem. Section 5. Future Forward. What's next for metals and composites? The world of material science is always innovating. For metals, research continues to push the boundaries with new advanced alloys, nanostructured metals, and additive manufacturing. Additive manufacturing, or 3D printing of metals, is revolutionizing how complex metal parts can be designed and produced, allowing for intricate geometries that were previously impossible or too expensive to make. For composites, the future is equally exciting. Researchers are working on faster curing resins, automated manufacturing processes, and out-of-autoclave curing methods to make composites more accessible. Smart composites with embedded sensors can monitor their own structural health, detect damage, or even adapt to changing conditions. Sustainable composites, including biocomposites and bio-based resins, offer greener alternatives to traditional petroleum-based composites. Improving the recyclability of composites is a huge research focus, with progress being made to recover and reuse these valuable materials. The push for a circular economy is driving innovation in how we design, use, and dispose of all materials. There's no single winner in the metals versus composites debate. It's all about the specific application. Metals offer proven strength, stiffness, and often lower cost, making them ideal for a vast range of structural and general engineering tasks. Composites provide exceptional lightweight strength, design flexibility, and corrosion resistance, excelling in high performance and specialized applications. As material science advances, engineers will have an even wider palette of amazing materials to choose from, leading to even more incredible innovations. Isn't science amazing?